Hello everyone and welcome. In this video I will talk about Python dependencies. I will review a case of a small application and when the Python codebase grows beyond one development team. I will show how to specify requirements, why and how they need to be pinned. There will be semantic versioning, again, why and how to leverage it. I'll talk about two kinds of software, end-user applications and libraries. What's the difference between them and what strategy to use to pin their requirements. And finally, I will talk a bit about how to make sure that the security vulnerabilities in the requirements are fixed in a timely manner. Oh boy, a big intro. Coming up. To start, let's figure out how to specify Python dependencies. Here I have an example of a Python application. Doesn't really matter what it does. It is important for us to know it provides command line tool for a user and also it is distributed via public PyPI. I created a virtual environment for this application with Python 3.9. This is our Python and if you look at the packages, it contains only those installed by virtual env tool. One of them, setup tools, that installs Python application. This package, setup tools, it provides a function setup. In this function, there is a keyword argument and install requires. And it accepts a list of strings. Okay, to illustrate you content of this variable, let me print it. And I love this trick. To stop Python application immediately, 1 divided by 0 will raise an exception. Yeah, the fastest way to stop execution of Python. All right, let's see what in our requirements is. So see, it's a list of strings. Each string is a requirement, which consists of the package name and version constraint. Okay, let's actually install this application. There are two ways to install it. We can use setup tools and run Python setup install. It will resolve dependencies, we'll install them from known indexes, and here we have click, log, utils, and pymysql. Alternative way to install Python application is pip. But I think it will just check that requirement is already satisfied and go ahead with installing the Python application itself. Pip provides some additional features on top of setup tools, so in some cases it's more convenient to use pip. As you can see, I listed my requirements in a file, requirements.txt, but in theory, of course, I could list them directly in here. Click pymysql and log utils. Okay. The reason I moved the requirements to a separate file is because there are other tools that work with requirements and it's just easier for the tools to parse a separate file, requirements.txt, versus parsing Python code and look for this list. Those tools are, for example, safety. Safety is a tool that checks requirements for security vulnerabilities and reports if there are some vulnerable versions. Another tool is pip-sync from pip-tools. It also helps with pinning versions of Python requirements, but I will review them later on. You might have noticed that I specified requirements with version constraints. And if it's an end user application, then ideally it's better to provide exact versions of your dependencies. This is an end-user application. It provides an entry point. But also I wanted it to be used as a library. That's why I relaxed requirements a little bit. I will review later on the difference between a library and an end-user application and what it means for dependencies, but later on, so stay tuned. I have another end-user application where I specify dependencies with exact versions. Let me show you. It's a backup tool, and each of the requirements has exact version, you see? And if this file looks like auto-generated, it's because it is. It is auto-generated by a tool called pip-compile. Let me show you what's going on here. Okay, let's go to our code. Okay. So this is my virtual environment. Okay, all dependencies are installed. Look what happens. I actually specify requirements I know in the file requirements.in. These are input requirements. Okay, I specify click, PyMySQL, I use Boto, so I specify Boto, and so on and so forth. Okay. Then, using this file, I use a tool pip-compile from pip-tools package. Okay, let me show you. Pip list, grep, pip-tools. There is a pip-tools package. It provides pip-compile tool. It takes requirements.in as input requirements, resolves the requirements. It also finds requirements of requirements and generates requirements.txt, where it lists every requirement that pip-compile has found. Okay, exact versions. So now when I run a test in my virtual environment, I know that the test passes with exactly this version, and if I package my application with exactly these versions of requirements, I have some level of confidence that my application will work. Now, how to install these requirements? In theory, we could do something like this. We could specify requirements txt, and pip would install these requirements. But there is another tool. It is also provided by pip-tools. It's called pip-sync. Let me show what it does. So let's say we have a zip requirement, okay? And let's say we have some older version of it. Let's say 330. Yes, I meant 330, okay? So here we have zip 330, and if we install requirements with pip, it will see that this requirement is already satisfied, and it will not change it. So, but in requirements we have, where is this? Zip, let's find it. Yeah, in requirements we have 340. So pip-sync will make sure that version in the virtual environment and in the requirements file is the same. Okay. So here it detected that 330 is installed, and instead it installed 340. Now let's review a use case. Let's say there is a company, a Python shop. There are at least 2 development teams. They write Python software. Let's review how Python software evolves and how different teams interact with each other. So we have team A. It develops application my app. Okay. It creates a Git repo. So we have Git directory, we have setup.py because it's setup tools compatible Python application, and we have a requirements file. So this application starts as end user application. It doesn't use any in-house libraries. It just uses some public requirements like requests, URL lib, PyMySQL, and so on. So this application lives its life contained within single repo for some time. But after a while, application grows in size, and at some point, the development team A realizes that, hey, this application contains quite a lot of useful classes that we can move to a library. And let's say we create my lib. Okay. It goes to a separate Git repo. It also set up tools compatible. It also have requirements. Requirements txt. Okay, so in this case, requirements txt in the my app will specify that, okay, I depend on my lib and the version 01. Okay, so this is library, this is team A, and my application. Meanwhile, team B develops their app that lives also in its own repo. It also supports setup tools, and it also has requirements. Now, this application also depends on my lib, and it lists a requirement my lib, and let's say version 02. Okay. So now we have one common library, 2 applications developed by 2 different teams. In terms of ownership, Team A started my app. It also moved some code out of my app to my lib. So it's natural that Team A owns the library as well. Team B, on the other hand, doesn't contribute to my library, it just uses it as a dependency. It is also possible that my lib starts living its own life. Let's say it became so big that we need a separate team to maintain it. So now we have team C. Now we have a communication and collaboration challenge. We need to make sure that team A, team B are effectively using library mylib that is maintained by team C or team A. Neither team B's application nor team's A application doesn't break when team C introduces any changes to mylib. Okay, let's see how we can ensure that. Now, if we think about version of software in general, we can come to a conclusion that a version is nothing more than a code that corresponds to a particular set of features of this software. Thus, version A is one set of features, version B is another set of features. But sets of features are not completely unrelated to each other. To codify this relationship, semantic versioning was invented. For example, if let's say we had version A and then we came up with version B. Version B may be totally different from version A. That means version B is backwards incompatible with version A. So features in version B are very different from features in version A, and version A and B cannot be interchangeable. Another situation is there is version A and version B is version A plus some additional features. So if my software depends on version A, I will be able to use version B because additional features of version B doesn't break my software. So that means version B is backwards compatible version. There is another situation when version A is a set of features, version B is same set of features, but we found a bug in version A, we fixed that bug, and that became a version B. So this is called, I don't know, patch version or bug fix version, and that's completely different from two previous cases I described. Now, semantic versioning defines a version as a string that comprises of three numbers separated by dots. The first number is called major version. The second number is called minor version. And the third number is called patch version. Okay, so example of a version could be 1 to 5, right? 1 to 5 is our version of our software. Now, if I develop a new version of my software, and this version changes existing behavior of the previous version, then I have to increase major version because it is a backward incompatible change. Incompatible change. And then I need to increase 1 to 2. If I create a version that adds a new feature, but it doesn't modify behavior of existing features, then it's a backward compatible change. Compatible change. And then I increase second number. 2 becomes 3. And another case possible is when nothing changes in behavior of my software, but I found a bug in the declared behavior, and I fixed that bug, and there is a new version that fixes that bug. In that case, I increase the last digit, and it's called bug fix. So this is the essence of the convention. Let's see how we can apply it to our use case. And before we do so, let's figure out how we can specify dependency version constraint. If I'm a developer of application and my application depends on library mylib, I can specify that my application works with mylib versions 1.1 and up, which is equivalent of 1.10, because we remember semantic version is 3 numbers. We can also exclude some versions. For example, we know that version 1.2 is buggy. So we require anything higher than 1.1 except 1.21. So in this case, 1, 2, 1, okay. But here's an important bit. Remember, the first digit of the version in semantic versioning convention means that it's a increase in the highest version means it's a backward incompatible change. So I know today when developer of mylib releases new version 2.0, it will include backwards incompatible change, and there is a high chance that my application will not work with mylib version 2. It makes sense for me to specify a range of versions. For example, I know that my application works with version 1.1, but I don't want to depend on version 2.0. Okay? And the equivalent of this would be much shorter notation, tilde equal. So that's this and these are equivalent. Now let's see how semantic versioning helps in this environment. I assume there are 3 teams. They're independent on each other. They have different priorities, different pace, different roadmaps. And they maintain their respective repos, but it is possible for team B to make changes to mylib, or team A to make changes to mylib. Let's make sure nothing breaks. Okay, so in this diagram, I should correct few things. First of all, my app and their app is an end user application. That means I need to specify, I want to specify versions exactly. So I don't specify range of version. I give the range in requirements.in, but eventually it becomes my lib equals to 0, 1, 5. Okay, and the same story here. It's not txt, it's requirements in, but our txt will contain my lib equal to 0 to 1. Okay, and team C is working on mylib. At some point, team B says, hey, Team C, could you implement a feature for us? Team C says, it's not a priority for us right now. Feel free to implement it yourself. So Team B contributes to my lib, and that becomes version 0.3.0. Okay. Now look, my app doesn't see this change. It tested with version 0.1.5. It packaged it with this version, and of course my app will not break just because my lib released a new version. But Team B can now depend on this new version. They want to upgrade, and they regenerated the txt file, which now becomes 0.3.0. Okay. Now, Team C was working on a big change. They merged it into the master, and that happened to become a backwards incompatible change. So they release version 1.0.0. Now, every time my app or the app upgrades versions, they will not use version 1 because it's backwards incompatible, and we have protection against backwards compatibility. So they will keep using version 0. This is called major version pinning, when we do not use next backwards incompatible change. But let's say that in your company you have a security vulnerability checks implemented in your CI system, and that check at some point fails if any of the applications use 0 version of mylib. In that case, next time Team B wants to release a new version of the application, their CI system will notify them that, okay, version 0 is vulnerable or outdated or obsolete, and you should upgrade. In that case, what they do, they test their software with new version. Let's say they Team B needs to make some changes to the application to make it work with version 1. They tested it, they upgraded the constraint, so it's 1.0 now. Okay, and when they regenerated requirements txt, that became 1.0.0. Okay. My app, owned by Team A, didn't break yet because they pinned to version 0. But next time when they release a new version of their software, they will be forced to migrate to version 1 and adjust their software. And note convenience here. If Team B needs a new feature and they are willing to invest their time to implement that feature in the library, they can freely do so without danger, without risk of breaking things in other applications like my app. At the same time, Team C has a mechanism to implement backwards incompatible change and not break any of the applications that depend on my lib, because they can increase major version and release backwards incompatible change in new major version. So that's a convenience that allows 3 teams work independently. At the same time, there is a mechanism to ensure check for security vulnerabilities. there is a mechanism for protection against backwards incompatible changes, and everything works in the most efficient way. Let's talk now about end-user applications and libraries, how they are different, and what it means in the context of version pinning. End-user applications is software that provides command line tools. These command line tools are used either by humans or by shell scripts or in cron jobs, etc. Libraries, on the other hand, used by other Python softwares. Example would be requests library. Both end-user applications and libraries can depend on other libraries. Like my end-user application can depend on requests library, and some library can depend on the request library. So let's see how we can how we specify dependencies in each of these cases. Okay. So from example before end-user application, let's see it's my app. And let's say my app depends on requests library. And there is a library, my lib, and it also depends on requests. Now, ideally, when I pin version, I want to be in the end user application as specific as possible. And the reason for that is because when I ran unit tests or integration tests, I ran them against some specific version of my dependency. And to make sure that my application works the same way as in the test environment, I want to specify exact versions of my dependencies. Okay, so in case of request, let's say I tested it with version 1.2.5. So I want to run it with version 1.2.5. Libraries, they are different from end-user applications in that sense that libraries are meant to be used in different virtual environments. And if my lib depends on requests, if I specify version exactly, by the way, it's double equal 1.2.5. It is possible that requests library will be used by some other library in other virtual environment, and the version constraint for that dependency may be different. Let's say some other lib depends on requests too, but let's say owner of that library specified version 1.2.6. Now, if you want to use mylib and tatlib in some end-user application, you have a version conflict because you cannot have two versions simultaneously. That's why in libraries you usually relax requirements. But how much relax? It's best practice to depend on the major version of the library. So if we tested it with version 1, we usually depend on version 1.2, let's say 1.2. So if other library was tested with version 1.3, then eventually in some other end user application, requests will be installed something like 1.3.5. whatever is available. Okay, so that's the difference between end-user applications and libraries. For end-user applications, you want to specify exact versions. For libraries, you want to specify a range of versions, and usually it's the version is pinned to the major version of dependency. In this environment, we also need to have another mechanism of upgrading requirements. And there are at least two reasons to upgrade requirements. Reason number one is if we want to use some new feature that is available in next version. Let's say my app pinned my lib to major version 0, but team A wants to use some feature in my lib that is available in version 1. Then team A reaches out to team C and says, hey, we want to use this feature. And team C says, that feature is available in version 1, you should upgrade. Then team A upgrades the dependency, they pin it to version 0, to version 1, and they change their application to make it work with version 1, and they release their new version with dependency on my lib version 1.0.0. It's also possible that team C deprecates support of version 0, and internally inside the company it communicates that, hey, version 0 is deprecated, you need to upgrade your applications to use version 1. And now team A and team B can independently upgrade their applications when it's best for them. They do not depend on each other, and they can do it in different moments of time. So that's the first big case when you may be required to upgrade dependency version. Second reason to upgrade dependency is security vulnerability. And that often happens with external dependencies. For example, your application depends on cryptography, and the cryptography package 3.2 is vulnerable, and you need to upgrade. So here I'm back in the end user application. These are my dependencies. They're pinned to exact versions. And you can see the scope of the problem now. There is absolutely no way I can manually keep track of security vulnerabilities of my dependencies. Fortunately, there is a tool to do that. It's called Safety. It's pip installable. And to check my dependencies for security vulnerabilities, I can run it with these arguments. So it shows me that my current requirements txt contains vulnerable versions. These are cryptography 3.21, and it shows that any version below 3.3 is vulnerable. If I incorporate this check into my CI/CD pipeline in Travis CI, then the very next time I submit a PR or I create a commit in any of the branches, my Travis job will fail with this security check, and I will be forced to upgrade dependencies. So that was all for today about Python dependencies. To summarize, code is separated into end-user applications and libraries. Semantic versioning is used to communicate changes outside, and to enable collaboration between teams. End-user applications are pinned to exact versions of dependencies. Libraries are pinned to the major version of a dependencies. pip-tools is a package that helps to maintain requirements.txt, and the safety tool enforces security upgrades of your dependencies. Next time I will configure code editor for maximum efficiency, and I will show how to use Vagrant in your development workflow and how to run quick development tests on remote development machine. So stay tuned and see you later.